for this experiment, I'm going to be evaluating this thing called the hydrostatic paradox. Basically, the idea of it being that the pressure as water, as the height of the water increases, pressure of course will increase. Of course, we've been learning that this semester. But in addition to that, mass does not matter. So the way I'm going to demonstrate that is water is going to go up to here on both sides. You would expect maybe that water would come out faster in this one since there's more water, but we're going to see that's actually going to come out at the same rate. So first, I'm just going to demonstrate that mathematically. Just from our equations we've been learning, using Bernoulli's equation. I'll write that down real quick. I'll draw the pipe first. So we're going to have this pipe. It's going to have a hole in the bottom with an initial velocity. Let's do 1. Okay, so initial velocity 1, and we'll have z2, z1. So we're going to have half squared z1g. Let's do that very well. For density equal to 1/2 v2 squared, same thing. Now, of course, density and pressure will be the same. You can cross those out. Velocity, this will be velocity 2. Velocity 2 is 0 because it's at rest, so cross that out. So V1 is going to end up being, when you do that algebra for all of that, it's going to be 2gz1 minus c2. Of course, right from the start, we can see it's not dependent on mass. You can do the same thing if you do the funnel with the hole there. Sorry, I didn't draw the hole. Still V2, Z2, Z1, V1. Same thing. Doesn't matter about this side here. And the reason for that in the hydrostatic paradox being that the force of the water pushing down on this funnel here, the funnel is actually going to be pushing back according to Newton's laws. So that force or that pressure due to the pressure on the funnel is going to be negated. All that matters is this invisible kind of line here for the pipe. So as long as they both have the same, you can just imagine that those are the same dimensions, but as long as they have the same diameter, everything should be good. So then I'll continue, go back to kinematics, which is good old physics 1 stuff. We'll have this plus E naught t plus 1/2 big T squared, just to see where the water will actually land, because it's going to go out here, of course. So we'll have this x value of the distance. So, let's see. Getting mixed up. Oh yeah. Oh, so we'll start with the y velocity, of course. The y velocity, it's going to be 0 because it's just coming out horizontally at 0. X or y naught will be, I'll count y naught as, what did I do? Oh yeah, y naught will be z2, y will be 0. 0 equals that plus, and then of course acceleration will be gravity, and that'll be something minus because gravity's going downwards. Then we will have, we'll solve that for t in order to transfer it to the x portion. So 2 over t. This is all this quick algebra that I did on my own, but now that we have t, we can solve for the x value. So x is going to equal x naught plus v naught t plus 1/2 t squared. Again, acceleration, the horizontal will be 0. V naught will be this, or v1, I guess I should say. And then x naught will be 0, since we'll have our coordinate system right here. So that's going to be 0. So our x, after I plug in t here, and then I plug in the v1 here, do all the algebra for that, and it will come out to 4 z2 z1 minus c2. So that should be theoretically the position of where the water will land. Again, nothing to do with mass. It's all down to the position of the height. So now that I have the map for that, I measured the height of there's like a little circle here, that'll be the hole. I measured the height for Z1, and then height for Z2 will be the top. After computing that out, the X should be about 11.2 inches. It should go that far. So now I'll demonstrate it non-mathematically, theoretically, so you guys can see what that looks like. This one, what I'm going to have you do is, since the water is going to like decrease a lot faster in this one, because there's a lot of water, I'll just have you pour water in to keep it consistent. Okay. Does that make sense? Okay. You'll use this. Had to bring a lot of water for this. Okay, so both filled to the same height. This one, of course, having a lot more water in it. I'll hold this one, and then I'll have you pour water in right when you start opening it, because it should start decreasing. Minju will just be putting water into this one because, of course, the water will decrease pretty fast. I want the velocity to stay somewhat consistent so you guys can see. But what James and I are going to do is just rip off this tape, reveal the hole, and as you'll see, the water from both, if you kind of see with the angle, the water should be going at about the same rate for both. Okay, ready? So as you can see, the water is about the same. Okay. Put the tape back on. You can put the tape back on. But, yeah, thank you. And that was my presentation.